Good morning, everyone, and welcome to another live Quanser webinar. My name is Murtaza, and together with my colleague Gemma, we will be your hosts and moderators this morning. Today, we are very excited to have Lorena and Kelly from Quanser's R&D Academic Applications team, which develops teaching content and research examples for controls and robotics to accompany our systems. In today's webinar, they will highlight the importance of camera systems in Quanser's products and demonstrate some of the capabilities of Quark's vision libraries using the QBot 3 and QArm.
Hello, everyone, and welcome to today's webinar, where Lorena and I will be introducing you to using cameras for vision applications with our Quanser systems. In today's webinar, we will start by introducing you to a few basic camera concepts. We will build upon this to explain some common Quark vision blocks, and then show you how these blocks work in 3 demonstrations using the Intel RealSense D415 camera. First, we will use the camera on its own, and then integrate it into Quanser's QBot 3 and QArm. Each of these demos will increase in complexity as they build upon each other. In each of the demos, we will walk through Quark's vision blocks used in the Simulink models and talk through the setup and the hardware. At the end of the 3 demos, we will briefly touch on some more advanced Quark blocks before opening the floor to all attendees for questions. Please feel free to put your questions into the chat at any point during the webinar. We would love to hear them. In order to get us started with some of our Quark blocks in Simulink, first, there's a few basics about how images are stored and understood by the computer that we need to get familiar with.
So let's learn a little bit about this. To manipulate image data, we need to have a basic understanding on how these images are understood by the computer. So in the computer, images are represented mathematically as matrices. A pixel's position is indexed in 2 dimensions as a row and column tuple. Consider the 5 by 6 grayscale image on the right, where the tuple 3, 4 represents a pixel in the 3rd row and 4th column. Once we understand how to index a pixel, we would also like to store information at that location. This information, such as color or light intensity, is specified along additional dimensions called channels. Representing grayscale information requires a single channel. However, when we represent colors, we need more channels. There are multiple ways to represent color information, which leads us to take a closer look at color spaces. Most images are normally represented in the RGB color space. For example, images taken by your phone camera or even your webcam. This color space is based on the additive RGB light model and uses the red, green, and blue primaries to describe the color spectrum in an image. In this case, the mathematical representation of the image is formed by a row and column for indexing, followed by a 3rd dimension with 3 channels, 1 for each color, red, green, and blue. And when combined, the 3 channels outputs a picture in color. RGB intensities are most commonly represented on a linear scale from 0 to 255, which is an unsigned 8-bit integer, or they can be represented as a float from 0 to 1. There is an alternate color space, HSV, where the 3 channels represents the hue, saturation, and value of each pixel instead of the red, green, and blue intensities. In this case, hue looks at the color of the pixel independently from the lighting conditions. Saturation represents the amount of gray in a pixel or the primary color mixing. And value describes the lightness of each pixel. HSV's intensities are linearly scaled as well. Some represent hue from 0 to 360 degrees on a circle, as shown in an image on the left. Hue can also be represented from 0 to 1 or 0 to 255 in some implementations. Saturation and values are scaled similarly to RGBs, either 0 to 255 in case of unsigned 8-bit integers, or 0 to 1 as floats.
In today's demonstrations, we will be using HSV to look for yellow color intensities. HSV is great when trying to find a specific color, independent of the lighting conditions in your environment. In this example above, you can see that despite the varying lighting conditions in the image of the road sign, the hue remains close to 3. The light changes can be observed in the other two channels, the saturation and the value. When using RGB, however, the amount of deviation in red, green, and blue intensities under varying lighting conditions complicates the process of picking the red sign. Lastly, note that since the value plane in HSV represents the lightness of a pixel, it directly serves as a grayscale representation of a color image. We can see this in the image to the right, where we highlight our object in the original color, but everything else is displayed using the value plane. Bitonal or binary images have binary intensities, where high is 1 or 255 and low is 0. These are the results of typical thresholding algorithms that return high or low depending on if the pixel matches the logical operation or not. These results can then be used as a mask to highlight different regions in an image.
Now that we have some basic knowledge on how cameras store the image data, we can now take a closer look at Quanser's QUARC vision blocks in MATLAB Simulink and jump into some demos to show you how they work. These are some of the most used QUARC vision blocks. We will explain them in more detail in the following examples. However, let me introduce you to some of them. The video capture blocks can be used for image acquisition from 2D and 3D cameras. You also have blocks for image filters and logic, as well as transformation utilities to rotate or manipulate the images. Another block that we'll be using is the image find objects block, which uses connected component labeling to find blobs for tracking. In our first demo, we will use the Intel RealSense D415 camera to detect an object of a specific color and track it around the image. This camera is the one that appears in the slide, and it appears in our QBot 3 and our QArm products and includes an RGB lens as well as an infrared-based depth estimation. The goal of the first demo is to introduce you to a few of the common blocks for vision, as well as introduce HSV and image thresholding. I will first talk a little bit about our QUARC vision blocks and what they're doing in this simple example. Since we are using an RGBD camera, we need a video 3D initialize and capture block, which will allow us to start our camera and decide the output format and its resolution. Once we get the image, we filter the image to smooth out the edges. The image filtering block allows us to do other types of filterings, for example, maximum, minimum, or even toggle filters. We then convert our image to HSV to be able to do proper color thresholding. Using the image compare block, we can select the range of values that we are interested in. This will output a bitonal mask image that we then filter to take the noise out. Using some image logic blocks, as well as the value plane of our HSV image to obtain a grayscale, we can create a grayscale image that will only color the areas of interest based on the mask. Don't worry, we'll show you this in the next video. Again, with our mask, we run it through the image find objects blocks, where we can select how many objects we're interested in, as well as the minimum size of them and how they will be ordered in the output. Finally, our video display outputs shows the image so we can see it while running our code in real life. Let me show you how this looks like. So as we can see, our color of interest in this demo is yellow. And as Kelly moves the object around the frame, it follows it. The mask shows where there's yellow in the image. We can see that when she covers the side of the box with her fingers, the mask just shows the area where the yellow can be seen. Since our find object box was meant to find only the largest object, we can see that it does not highlight the smaller object until the bigger box is out of the frame. We will now build upon this demo by incorporating it with our Quanser products. In the next demo, we will use a QBot 3 to track the same yellow box.
Using our QBot 3, we will now expand on this first demo that Lorena showed you. The QBot 3 is one of our autonomous mobile robots used to teach kinematics, mapping, and localization, as well as computer vision. In this demo, our QBot 3 will rotate to track our yellow box. The goal of this demo is to demonstrate how we can incorporate image processing with our hardware for real-time monitoring. Based on the location of the object of interest, the QBot 3 will turn to keep the object in the center of the frame. This is a useful building block for other applications such as line following or lane keeping for self-driving vehicles. Since this demo is a little more complex, we have things separated by subsystems. However, there's a few things to highlight here. First, we have our Quark Hill initialize block. This block allows interfacing between our MATLAB model and any of our products. So we always need one of these when using Quanser products, whether it's hardware or software. In this example, we can also see blocks that return the sample and computation time in our model. It is vital to keep the computation time lower than the available sample time so that real-time performance constraints can be met at each sample iteration. In this example, the motor I/O is executed at a faster sample rate than image processing, which is why we have two pairs of time blocks to monitor each sample rate. The QBot 3 inverse kinematics and motor command subsystems send velocity information to the robot. We will focus on autonomous subsystems that will allow us to do image processing. So let's look how this works. The first part of this algorithm is similar to what we saw in the previous example. We transform the image to the HSV color space and then apply a threshold to pick our color. This looks a little different as the threshold block is now using external inputs, so you can tune values programmatically if needed. Lastly, we run erosion filters on the binary output of the color threshold to reduce noise and then pass it on to the block to detect blob information. Finally, we will monitor the live video feeds using video compressed displays. So let's see this in action now. In this video, we can see that the mask showing the object of interest is present. So the other video on top is the real-time camera output. Our example tries to keep the center of the object in the center of the image. We can see that as Lorena moves around the robot with the yellow box, the QBot 3 moves to follow it. As we can see in this demo, the height or the vertical position of the object in the frame doesn't really matter. In this case, we only care about the horizontal value of the center of the object, as the QBot 3 is fixed on the ground plane. The robot will only move when the object's center moves horizontally. To keep the robot safe from sliding off the table, we did not do anything based on the distance to an object. However, it's totally possible to implement a solution where the robot also tries to always be a certain distance from the object. This is thanks to the depth component of our camera mounted on the front of the robot. Our next demo with the QArm will demonstrate something similar.
This next demo will use our 4 degree of freedom serial manipulator, the QArm, to do some visual servoing. This QArm was designed to teach manipulator kinematics, dynamics, and vision to university students. In this example, we will show you how the arm can follow an object in 3D space using our RGBD camera. The goal of this demonstration is to build upon the previous QBot 3 example. The QArm will now track the object both vertically and horizontally, and additionally move towards or away from the object of interest to maintain a safe operating distance. This is one of the vital building steps towards perception stacks for cobotics applications. So the Simulink diagram for this example is a little bit more complex. However, there's been a full webinar in the past that talks through this example, the considerations for this, and its uses. You can find the webinar on our website under the name Follow Me. However, here's a quick note about this one. As we can see in the center, in the red image acquisition subsystem, we not only use the RGB image, but also the depth to be able to figure out the different locations and distances to the object. And we then use forward and differential kinematics to figure out the desired position of the robot. Let's see how this looks like in real life. In this video, we can see how the arm is capable of following the object in space, and not only turn to where it is, but also maintain a specific distance from it. Let's see that happening. We are able to do this thanks to the depth information we get from the camera. The video in the middle is the Simulink output, where it shows how far the center of the object is from the middle of the frame. The arm then tries to compensate for this by moving around in space.
For the last section of this webinar, we wanted to highlight the numerous additional blocks that are available to you with QUARC. So here are some of them. These blocks will allow you to compress or decompress an image, find April tags or localize them in world coordinates, fix image distortion, align depth and RGB data, calculate optical flow, and more. With the RealSense cameras, the depth and the RGB coordinates are not aligned, and the image align block can help you offset that misalignment. A tool very useful for RGBD applications, such as our QArm's visual servoing demo. If you have any questions about these or any other blocks, they are all documented on our QUARC help page. The QUARC help page can be found by right-clicking on any of the blocks in the library browser and clicking on the help button in the menu. If a block is already in your Simulink diagram, or if you need help with the parameter inputs, the help page can be found by clicking the block and selecting the help button at the bottom of the pop-up window.
To summarize, in this webinar, we talk about how images are processed digitally and the importance of cameras for different robotic scenarios. We then ran 3 demos in increasing levels of complexity to be able to understand image processing and what can be done with our Quark vision libraries. After introducing some camera basics, we did visual servoing with 2 of our Quanser products. We first used the QBot 3 to do object tracking in 1 dimension, and finally we used the QArm to do object following in 3 dimensions. And that's it from us. Please feel free to ask us any questions.
Thanks for the great presentation, Lorena and Kelly. I think we can proceed to answer the questions that have come from the audience. So our first question is, do you need additional drivers to use the RealSense camera on Quanser devices?
I can answer that one. Devices that come equipped with the RealSense cameras already have support for them via the RealSense library, such as the QBot 3 or the QCar. We also have support for it in Windows if you have Quark installed, so you can use it with devices such as the QArm or directly by itself as well. We're gravitating towards providing support for RealSense cameras on our robotic platforms as well, even though they do not come equipped with one, because the technology is very relevant to robotics and machine learning.
Thank you,
That
Kelly.
answers the question.
Given the displacement between 2 lenses on the RealSense camera, how can you estimate the depth to an object that you detect by the RGB image? I can take this one. The advanced Quark blocks allow you to align the depth image to any other image whose intrinsic properties are known. This way you can align the depth image from the RealSense camera to its RGB image, and then use the aligned depth image to estimate object coordinates using standard image theory. Our next question is, what options are available to monitor the real-time performance of our vision applications?
In addition to sample and computation time blocks we demonstrated during the webinar, you can also use the computation time blocks with a function called subsystem, which is a block in QUARC, to monitor the computation time of a specific algorithm. If you have a QUARC monitor connected to your target, you can also launch a console, which will let you know if your thread sample time is being exceeded for embedded applications.
Thank you. And the last question we have here is, in what situations would you use the RGB color space instead of HSV?
I can talk about that one. There actually isn't a time where RGB is better than HSV for computer vision tasks. The RGB model was made for your display screens, and it is actually easier to visualize and understand for teaching introductory vision. However, the HSV model mimics the way we interpret light and color as humans, and its ability to distinguish chroma and lumina is far more effective for computer vision tasks.
That's all the questions we have today. This brings us to the end of our webinar. We would like to thank Lorena and Kelly once again for the great presentation, and a big thank you to everyone who attended today. Please visit our website at www.quanser.com and our LinkedIn page to find out more about our systems and upcoming webinars. Have a great day, everyone.